Next. Cylindrical capacitor. You saw maybe all electrolytic capacitors are cylindrical capacitors. A cylindrical capacitor consists of two coaxial cylinders of radii A and B. Separated by a dielectric region. For us in electromagnetic fields, beyond waves, we go to transmission lines. Earlier, we had in communication engineering parallel wire transmission lines being used. Nowadays, wherever it is the wired structure that takes the signal from one point to the other point, by default, it is coaxial cable. When you say it is transmission line, it is a coaxial cable for us. All the electrical properties of a transmission line depends upon a set of basic parameters defined. Resistance, inductance, capacitance, conductance per unit length of that particular device. Ultimately, to go to a position where for a particular application, you need to design a coaxial cable. You should know the way in which the dimensions and the medium used affect the basic parameters of the transmission line. So we need to derive the expression for the capacitance of a coaxial line, which is as a capacitor, a cylindrical capacitor. This is of radius A. This is of radius B, with epsilon present between the region between these two cylinders. Let us suppose we consider this to be of length L and epsilon the permittivity of the medium. Again, to determine the capacitance of this capacitor, we assume a charge of plus Q on the inner cylinder, uniformly distributed over the curved surface of it, and minus Q on the inner surface of the outer cylinder, with plus Q on the outer surface of the inner cylinder, right? Minus Q on the inner surface of the outer cylinder. To determine the potential difference between these two conductors, we need to talk about the electric field intensity. To determine the electric field intensity in the applications of Gauss law, I told you that at any distance r, if you want to rho, actually it is in this coordinate system. At any distance rho from the axis of the cylinders, if you need to find out the field intensity, first of all, draw a cylinder of length L passing through that point of interest, having the axis of these two cylinders as its axis. So the flux density at any point on this cylinder is fixed and given by Q by 2 pi rho L. Correct? 2 pi rho L is the area, curved surface area of the cylinder. 2 pi rho L. A rho. Here it is non-uniform. You know that the lines diverge. They are not parallel set of lines. D bar is equal to Q by 2 pi rho L A rho. E bar at any point is Q by 2 pi epsilon rho L A rho. The potential difference B between these two cylinders is equal to what? Minus integral B to A, because I need to principally work against the field force. B to A, Q by 2 pi epsilon rho L A rho dot DL is what? D rho A rho, because I'm just changing rho, which is equal to Q by 2 pi epsilon L integral B to A. Sorry, A to B I will put now. Minus I will remove and say A to B D rho by rho. Natural logarithm of rho, ln of rho from A to B is ln of B minus ln of A is equal to Q by 2 pi epsilon L. Ln of B minus A is B by A. Perfect, it is positive quantity. B is greater than A. So many, units, volt. Now Q by V, the capacitance of this capacitor is 2 pi epsilon L divided by ln of V by A. In the case of coaxial cables, the basic parameters are defined as per unit length quantities. This says the capacitance per unit length of this capacitor. For length L, it is L. Directly proportional to L, it is what it is telling. Is 2 pi epsilon by ln of V by A. Keep observing these things. They are all wonderfully helpful to us. We will be in a position to really appreciate these things in a better way when you go to transmission lines and all. So many farads. Spherical capacitor. This consists of two concentric metallic spheres of radii A and B. With a dielectric separating these two conductors. To determine the capacitance of this capacitor also, we assume a charge of plus Q on the inner cylinder sphere and minus Q on the outer sphere. Just for the sake of looking into it, normally we don't use these things. Again, in between these two spheres, we saw in the applications of Gauss law that the field is spherically symmetric. So to determine the field at any distance r from the center, we need to draw a spherical surface which is everywhere perpendicular to the flux lines, because of which the flux density d bar is equal to Q by 4 pi r squared AR, because it is radial. 4 pi r squared is the surface area of the sphere of radius r. D bar is Q by 4 pi r squared AR. So E bar automatically is Q by 4 pi epsilon r squared AR. By r squared, it is telling that it is decreasing with the distance, right? Inversely proportional to the distance it is. And the potential difference V is equal to minus integral B to A Q by 4 pi epsilon r squared Q by 4 pi epsilon r squared AR dot exactly against I'll go dr r, which is equal to integral b to a. Okay, I'll just bring those things out. Q by 4 pi epsilon minus 1 by r squared dr. Integral minus 1 by r squared dr is 1 by r, which is equal to Q by 4 pi epsilon 1 by a minus 1 by b. Correct only. A small, because of which 1 by a is greater. I should get this potential difference because I know that I'm working against the field. It should be positive. Even in the cylindrical case, right? We saw that it is positive. ln of b by a. B is greater than a. Anything, logarithm of anything greater than 1 is positive. Less than 1 is negative. Okay. So the capacitance is what? C is equal to Q by V is equal to what? 4 pi epsilon AB by B minus A, so many farad. I think you know that this can be written as Q by 4 pi epsilon B minus A by AB.
So, will the potential inside the sphere will be V?
Potential
inside at the center of the sphere, the spherical capacitor, will it be V?
Yes, ma'am. With respect to the outer surface. Inside also it will be V because there will be no field inside.
Okay, so but potential is V, but the D is 0.
There is this.
I mean, inside that.
The potential has no dim. Potential has only dimensions. There is no distance term in potential.
Okay.
Q by 4 pi epsilon. See the potential expression. Q by 4 pi epsilon D minus A by AB. D is not there, ma'am.
Okay, so no, because I'm thinking like E is equal to D by epsilon, right? So if electric field, if it is like.
No, the electric field will not be there inside the inner sphere.
Yeah.
It's only for, maybe, because I discussed it, I did not talk about it.
No, because the formulas are like.
Check it now. E bar is Q by 4. In both cases, A less than or equal to R, less than or equal to B. In between only we spoke about. I spoke about this in Gauss law applications, because of which I just kept aside in the region.
No, so that I am like potential when it is coming, it is becoming.
No, potential is whatever they say.
Okay. And sir, electric field in between this inner sphere and outer sphere remains constant everywhere.
No constant, ma. It's not constant by R squared.
Like,
It's spherically diverging. It's not constant. The number of lines is fixed. When they are starting from the surface of a smaller surface area, because of which flux density is more, and they diverge and go on to the surface of the larger surface area, because of which it is least. In between, it continuously decreases. Flux density decreases inversely with R squared, actually.
Yeah, okay. So even V also varies.
Potential with respect to negative charge also will vary, no doubt about it. But what I am looking at is potential difference between these two conductors. If I want to know the potential at any capital R in between, what is that I have to do? B to R only I have to do. Okay. If I want to know the total potential difference, I have to integrate it from B to A.
Okay, sir. Thank you.
Yeah. Please check. This is extremely important. And we are expected to remember this. No, there is no need actually. We can derive it in no time. From here only, you should basically get accommodated to that procedure actually. If I want a formula, I will derive it in no time. 2 pi epsilon L by ln of B by A. This we are going to see. as the capacitance per unit length, basic parameter of the capacitor, of the coaxial cable, with inner conductor of radius A and outer conductor of outer sheath of radius B. They are all cylindrical conductors.